Hello, this is FlippedHarber for Precalculus. In this video we're going to talk about Moffs Theorem and complex roots. Now our objective for this video is to use Moffs Theorem and to find the roots of complex numbers. Our outline will talk about what Moffs Theorem is, we'll talk about using that theorem, we'll talk about how to find complex roots, and then we'll look at some examples of it. So, Moffs Theorem is used to find powers of complex numbers in polar form. Now, this is another example of why we bother putting complex numbers in polar form. Finding a power of a complex number is a lot easier when it's in polar form, thanks to Moffs Theorem, rather than when it's in rectangular form. If it was in rectangular form, I would probably bust out Pascal's triangle. I'd have a whole bunch of different powers on I to deal with, and this is just flat out easier. If I want to put a power on a complex number z, I simply put that power on the radius, and then I multiply that same power to the angle in both cases. Now the only condition here is that n is bigger than or equal to 1. So don't try to use Moffs Theorem for powers that are lower than 1, because really a power that's lower than 1 is a root, and we've got a different way to deal with that. So this is only for actual powers. Now obviously we should look at an example. So here's an example where we want to find the complex number with this power of 5. And we're going to go ahead and leave it in polar form. So, Moffs Theorem just simply says that I should take the 1/2, put it to the power of 5, and then multiply the 72-degree angle by 5. Pretty easily done. 1/2 to the 5th power is 1/32. 2, 4, 8, 16, 32. Pretty easy. And when I multiply 5 times 72, I get 360. So my angle on both of these is 360 degrees. Now, I like to go ahead and change it because technically, given the choice between doing 0 or 360 degrees, we want to do the 0. So we'll go ahead and change the 360 degrees to 0. But leave the sine and cosine in here. Yes, the cosine of theta is equal to 1. The sine of, the cosine of 0 is equal to 1. The sine of 0 is 0. But leave them like this. Leave the sine and cosine. Okay, so taking a complex root, again, is a lot easier in polar form. It's still kind of complicated though, to be quite honest. If we want to take roots of complex numbers, it creates several complex numbers. Well, it actually creates as many distinct, that means as many different complex numbers as the root that we're trying to take. So if I want to take the 4th root of a complex number, that's going to create 4 different roots that I need to find. And this is a lot easier in polar form. So here's a rather nasty looking equation. Go ahead, pause the video, write it down, and it's going to make a whole lot more sense when we actually use it. Okay, that k equals 0, 1, 2, 3, blah, blah, blah. Looks very confusing. It's not once you actually start to use it. So take a second, pause the video, write this all down, and then we'll take a look at an example. Okay, so let's find the complex 4th roots of the complex number square root of 3 minus I. Now, we're going to express our answer in degrees. Why degrees? Because that's what the homework says. If it doesn't say express your answer in degrees, then go ahead and express it in radians. But this one says to use degrees. Now, really the first thing I need to do before I find my 4 roots. So I'm actually finding 4 different things here because I'm finding the 4th roots. I'm finding 4 roots. Z sub 0, Z sub 1, Z sub 2, Z sub 3. That's the K values that I'm using. I always use 0, 1, 2, 3, and I stop one number shy of the root. Okay, that's the whole n minus 1. But before I do this, I need to put it in polar form. I do not want to tackle this problem in rectangular coordinates. Much easier in polar form. So I need to spend a little bit of time changing the complex number to polar form. You should have watched the video on that, so I should not really have to go through this too much. It's equal to 2 cosine 30 degrees plus I sine 30 degrees. So now let's find my 4 roots, z sub 0 through z sub 3. So here I've tailored that equation that you saw a little while ago and you should have written down. I've tailored it to this problem. Z sub k. Now obviously I've got to do this 4 times. I've got to find z sub 0 through z sub 3. This is my generic form here. It's a 4th root, so I'm taking the 4th root of 1. Why? Oops, that should say 2. That should say a 2 right there, not the 4th root of 1. Oh well, get over it. Make sure you write down 2 right here. And then I've got my 30 degrees divided by 4. Again, I'm taking the 4th root, so that's why I'm dividing by 4, and that's why you see the 4 here as well. Now I'm going to plug in my different values for k, 0, 1, 2, and 3. So, again, this should be a 2. Get over it. So now z sub 0, well, if this is 0, this whole fraction is 0, so it just totally goes away. Z sub 1, now my k is 1, so now you see that 360 divided by 4. And z sub 2, 360 times 2 is 720. Z sub 3, 360 degrees times 3 is 1080. Now I should combine my fractions. So I want to combine those fractions, and I end up with z sub 0 is equal to, now this should say the 4th root of 2, not 1. And when I actually reduce my fraction down, my fraction for z sub 0 is 7.5. Z sub 1, I get 97.5. Z sub 2, 187.5. And z sub 3, 277.5. So 4 different numbers when I take the 4th root of that complex number. Okay, so time for you to try some of this on your own. I'll see you in class, and I'll see you online.